All right, good afternoon, everybody. How you guys doing? Doing all right? You guys are really quiet. It's like my undergrad class. I mean, maybe it's because it's lunchtime or a big class, but they're always much more chattery. You guys have other classes before this one? Just kind of, okay, little fried or just kind of, just afternoon? Okay. Okay. All right. Well, I want to pick back up in this example, and thank you, by the way, for the feedback. I read through each of the notes, so if you didn't turn one in, I'd be happy to get your feedback paper at the end of class today. And I'll try to give you some more opportunities to give me feedback like that or about a particular topic. So please feel free if you notice something you'd like to say or like to communicate, don't hesitate, and I'll try to prompt you on occasion to draw that out of you. Okay, so last time we were working on this, and I got myself slightly confused as I was thinking about it. And the reason was I looked at the wrong control volume. So we had been solving this problem. We'd gone through this. That all was making some sense. We realized we had to figure out essentially what the ultimate reaction term was in here in order to move forward with the solution, and so we did that. Then the next step was to solve for, if we take a look back at the problem, we needed the solids concentration in 3 spots. We needed it in pipe 3, pipe 6, and pipe 7. So once we got it in pipe 6, then we knew it in pipe 7, so that was not too much of a problem. But then, and that's kind of where we started with a mass balance around the entire thing. Then we need pipe 3, and at first I was thinking control volume A, and I realized if we have an input and an output that would give us 3, we also would then need to account for the growth rate, so the reaction rate in the solids basin. And it's possible we could do that, but it didn't seem quite as convenient as if we did, when I thought about it, to ignore the reaction completely and just do control volume C. So no reactions going on there, but we still have enough information to find what we need. So if we look at control volume C, we've got 3 coming in, 4 going out should be 0, and so 5 going out is the only other piece, and we already have that information. So what's going in is going out, and it should be a rather simple solution, and I simply did not make that clear to myself, apparently, so I wasn't making it clear to you either, that we ought to, instead of doing what we were working on, I'm going to say control volume C means we have no reaction, and we have 1 input and 2 outputs. So with that, let me just give you a moment to resume there and make sure you're on the same page with me. If we're given that the concentration of our solids in 5 and 6 here, it's really also equal to 7, if those are given at 9.8 grams per liter or 9,821 milligrams per liter, what do we expect from 3 in terms of the concentration? So the concentration of solids at 3 is what we're solving for. So give that 2 to 3 minutes and see what you can do. And remember, we've got the flow rates for each piece right here. about ready. So hopefully what you saw is we can set it up rather simply about we had a steady state assumption last time, so we say 0 is our net accumulation of solids in the system, and we're going to have then inputs being the Q3C3, that's how much solids are coming into the clarifier, and then we also made the assumption that 0 are making it out the top of the clarifier, so 0 are in part 4, excuse me, here. So then basically what's going in is equal to what's going out, but the only place it can go out is pipe 5. So we can set it up so that what's in 3 is equal to what's in 5. C3Q3 is equal to C5Q5, deriving it that way because C4 is 0, so that term goes away. Then divide both sides of this remaining equation by Q3, and we have all those flow rates, should have all those numbers. And while I was giving you a moment, I just went ahead and popped that into Excel, and we get an answer of 982 milligrams per liter. Okay. Does it make sense? All right. Okay, so I'm sure that we could have used a different control volume to find that, but this way is rather convenient. Don't have to worry about a reaction term or do any additional calculations aside from just that there. All right, so I have more slides in this set, but I also have them in the next set. So I'm just going to end this set of slides here and then pick up the next one. Any questions about this problem? It's in the book, so you can read through their solution. I wanted to walk you through it. And in some sense, we're getting ahead of ourselves, but I wanted to give you this flavor of, hey, this is how we can pick apart a problem and identify each piece that we might need. Okay, so I want to talk about how we are really assembling a mass balance kind of from the basics. So we're going to start with what we call the storage term, and this would be where are we what is it that we are describing that contains the stuff that we're interested in. So if we have these solids, mathematically speaking, we need some storage of it, that volume, but in this case we're going to describe a storage term as the really, really small discrete volume that we're going to describe. So when we think of the mass of some species I present in solution, we're going to take an arbitrarily small, or differentially small as the book says, volume, dV. Okay, so if we are trying to figure out how much of some substance is in a volume, we can split it up into tiny chunks and understand what's going on in each of those tiny chunks, integrate over all of them, and get our answer. So maybe a good way to think about it is the little building blocks toys here, right? So if you consider, you might be interested in how much red color is in the total set of blocks. You would realize, okay, some of them are pure red, so we'll maybe give that a value of 1. Some of them are orange, maybe that's 3/4 red for each block. And some of them are yellow, maybe that's half or less. Some of them are purple, so we're getting some red there. Some of them have 0 red. Well, when we divide all these up into each little storage terms, and we know how much is in each one, when we integrate all of that, we can come up with a number of total amount of red across that solution, or that volume, that total volume, okay? So each little block would be kind of an analogy to the storage term. Okay, so it's just a fancy way to describe what is dV, and this kind of tells us a little bit of something about what we need to do in order to understand a system properly to model it mathematically. Maybe we have cases where our reactor is not actually ideal. So particles, maybe we're chlorinating a bottle, but if I just drop in a little bit of chlorine, maybe you can almost, you've done this probably with milk and coffee. You can see there's a little plume of the cream, but it doesn't really spread everywhere if it's not mixed well. You could even introduce a little bit of mixing and you see swirls and it kind of looks cool. So, well, what if I want the chlorine to go everywhere, but it's not mixing as well as I thought? Okay, when we think of how to model that in a real situation, our reactors are not always designed perfectly. In fact, they're never truly ideal in practice. So that's where understanding this building block kind of idea is very important. So ultimately, we want to determine the total mass of I in the entire control volume. That's what we're saying right here. And if that's our goal, we need to understand how it's spread throughout that total volume. The way we do that is with these storage terms, okay, this concept. So we would integrate the mass of I in some volume V, and we would say that's equal to the concentration, the integral of the concentration times dV. Okay, and the reason we are going to take that approach, or we could take that approach, is because things could get messy. Now, this is kind of a fun little GIF I found, and what it's really showing is a few different processes. First of all, it's a little mesmerizing, so you're just going to get, hypnotized if you just stare at it too long. But you'll see in parts, if there's no other motion going on, there is some diffusion, some random walking of the molecules, and you can imagine if there weren't these little spurts of whatever, then it would probably slowly spread out, okay? Then we have, so that would be diffusion. Okay, so we have diffusion, have some understanding of that. Then we have advection. So each time you see one of these little spurts, it's almost like we're introducing some velocity or flow rate suddenly and it goes, right? So each time that happens, we would call that advection, where the water is physically moving, and so whatever's in the water is therefore moving. Okay, it's like flowing in some direction. Now, there's one other term here that's called dispersion. So if you look beside these spurts of water, you see all this eddying and other random things that are happening. It's not the slow diffusion of molecules, and it's not exactly one direction, but it's a little bit more chaotic, and it's causing some mixing and spreading stuff around. So that would be dispersion. So I'm mostly putting this image so that you have in your mind what we're talking about if we do need to understand thoroughly what's going on in a reactor. We would need to account for all three of these. Now to be quite honest, this is not my realm of expertise, and we're not going to deal with this type of like the hydraulics and stuff, hydrodynamics of our systems to a great deal, in part because I don't have I'm not as familiar as you probably get from some other classes, so that's just not going to be my focus here. But as we think about reactors and how we're setting things up, all of this can and will be at play to an extent. So we're going to see some math that if you need to account for all of this, it gets a little bit hefty, or at least you're working in 3 dimensions all the time, when if we can make some assumptions, maybe we will work in fewer dimensions. Okay, at any rate, if we take that storage volume, when we're trying to find the mass in volume V, well, we can take it, and really what we're interested in is the rate of change. So if we take the rate of change of that mass, V, as dV dt, or the concentration in that volume per time, this is getting closer to what we would, on a simple level, say dc dt in some volume. But if we needed to account for all this stuff, then we need to break up the volume into chunks. So that's kind of the point here. Okay, my notes should have had this all erased. So let me just check something real quick. Let me cancel that. Can I cancel that? One second. I think the notes that I'm using, that's frustrating. There should be a clean copy on Moodle for you, and that should have saved and uploaded, but I think okay. So what we're going to do. Sometimes OneDrive doesn't update properly, and then it's frustrating. So let me see if I can fix that real quick or erase the old. I'm just going to grab it off Moodle. Sorry, this will take me just a moment.
It seems clean.
On Moodle, it's clean?
Read it. It has those notes, and then there's the rest of it.
That's which file?
The only PowerPoint slides, the math balance slides.
Well, let's show you what I'm looking at to see if maybe I forgot to upload it here too, which would be annoying. So this one should be...
Yeah, the first one is...
I should have marked this as ready to view, but maybe I just forgot altogether. Let's see. Okay, that was not today. Okay, I apologize. This must have not gone through. Of course, I will... This is the slide set. I'm just going to do a real quick edit here. And I'll repost this for you, and then we'll be ready to go. And in fact, I did more edits. So I apologize. This is going to be... slightly different than what I had prepared. But we'll deal with it. All right. Okay, so if you wanted to follow along there, I just updated those slides. Here we go. All right, so I apologize for that. Some of my updates have gone through and some of them have not. So I think my system didn't finish updating or something. Anyhow, we'll work with it, and now it's clean for us to talk about and write any new notes. So all this to say, we have these different ways physically our contaminant or our species of interest may be transported through a system. And again, these will be the advection, diffusion, and dispersion. So to provide proper definitions here, advection would be the mass movement with flow. So as you have flow going through a system, that's your advection. Diffusion would be mass movement by what we call Brownian motion. It's kind of the random walk of molecules or particles around. You'll remember that has a lot to do with temperature, a lot to do with viscosity in terms of to what extent they're going, size of the particles, all that. And then we'll have dispersion, which is a mixing differences due to different flow rates in the system. So in this little diagram here, these guys would be advection, the solid lines. Diffusion could cause things to be going in the reverse direction. And by the way, this is a one-dimensional look at it, or maybe two-dimensional. So this here would be an example of diffusion, where it could be some backwards travel could be happening, even though the flow is going in one direction. Diffusion will also be spreading it out backwards. So it might not be making a net progress backwards, but it would, if you're watching this stuff flow through a system, some of it would just be going slower than the flow, effectively. And then you have the dispersion, and that's if you encounter some difference in the structure, some other forces, maybe some drag forces at the edge of something, maybe an eddy, something like that could cause some dispersion within your system. Okay, and that's true even if you have a laminar flow, so in a plug flow, kind of like a pipe or something, you still expect some dispersion, and it's not going to be a truly ideal scenario. Okay, at the end of the day, no matter what we are talking about or doing with respect to how mass is changing in our system, we're always going to come back to a mass balance principle of what's changing, what mass per time change is occurring. So anytime we're dealing, if we do anything with kind of diffusion, advection, all that, it's ultimately coming back so that we can do a mass per time or potentially number per time type of thing. So we're often going to assume we've got well-mixed scenarios with perfect mixing and no dispersion. We have another example on that, example 1, 2. And sometimes we'll make a steady state assumption where our net accumulation rate is 0. Now, we're not always going to make those, but those are common assumptions to make. And as you kind of have the idea now, if we need to take care of all the physical transport, all these other phenomena in 3 dimensions, and then look at that over time, that itself gets to be a pretty intense task. So I want you to know that we can, and I want you to know what it looks like, what it would take to do that, but not necessarily that we are going to do that all the time. Okay, so on that note, a little bit about what it would look like. So here we have a schematic kind of showing a distance from some surface and a gradient, concentration gradient, that if we were to model this mathematically, we would say that our flux J, providing a net transport into or out of, or net transport across the boundary of our control volume, transport of I, we would define it in this manner. We would say that flux, the net flux, would be equal to a flux due to diffusion times that area that's coming in minus what's going out. sorry, that's might not just be diffusion there. And we could expand that and look at each component, right? So I'm just giving you a picture that this is expands pretty quickly when we need to look at all three factors. And then this is just one going across one axis. So if we did this in 3 dimensions, it expands even more. Okay, so just kind of painting a little bit of a picture there. Okay, when we talk about our chemical reactions, we often have systems that are dependent on the amount of concentration we have. So C being our concentration of I. Well, if we have some chemical reaction, chances are it depends on how much we have, if it's first order or second order or somewhere in between. So if we had some catalyst surface, or if we had some, like I said, the chlorine in a reactor, well, it matters a lot where the molecules are and whether or not they're dispersed. So we can talk about 2 different systems, one being sort of a bulk or batch system, and the other being at some surface. And we have essentially 2 different descriptors depending on which one we're doing. So we will define a well-mixed system where our analyte of interest is well-mixed throughout. We would describe that as homogeneous, right? Especially in the case where we don't have more than one phase. If we had solid particles that are also well-mixed, well, then we have a solid surface and a liquid. Then we have 2 phases, okay? So if we have a surface of any form, so really it's an amount of phases. But typically in water treatment, we're going to be talking about a solid surface or just liquid phase. So if we have something dissolved, and we're going to ignore like the sides of my bottle, then if it's dissolved, it's homogeneous. If there's a catalyst surface like this or something, we would call that heterogeneous. Meaning we have 2 different phases. Now this becomes important because if we are considering where the reaction is happening and how much concentration is able to undergo this reaction, well, that's when surface area becomes important, because that tells us how much within this total volume, how much of it is useful for that reaction to occur. So here what we're introducing is for a homogeneous reaction in sort of a bulk fully dispersed, and I'll just go ahead and add a little here. It's only one phase. And we could also talk about that in the gas phase, right? A gas is also a liquid, so it's going to work in the same type of manner. If we just have a gas and no surfaces and some reaction going on, that would be a homogeneous reaction. Pass it through a catalytic converter, suddenly now you have a heterogeneous system where you have the gas phase and a solid phase. Okay, now the control volume is simple enough in our homogeneous phase where we have some reaction R in the volume within that storage term, okay? And we're going to integrate over the entire system. Now, when we do it with a solid surface around, here's where we change things up a little bit. So to understand what's happening at the surface, we need to add in something about how much volume is occupied by that surface, or how much effective volume is useful given that surface. So what we're going to do is we're going to account for that surface area. I'm going to read just a bit of this. So the rate of the reaction occurring at the surface might be quantified by a term, and they're using R of I, so that's the reaction of I, some species that we're interested, with a sigma, just pretty small there, but that's a little sigma, indicating the rate at which I is being created per unit amount of surface area present. So depending on how much surface area we have, that's going to dictate how much reaction can occur. So that's what we're making this on a basis of surface area present for that reaction to occur. Okay, so then the corresponding term in the mass balance would be R I sigma times A dV, where A is the surface area concentration in the system. So that's a strange one, right? So A is surface area concentration. Really what that means is surface area per volume. So it sounds really strange to say a surface area concentration, but if you talk about it, let's say adding some powder, and you know that powder has some surface area per weight, and you know how much weight you added, suddenly you have some amount of surface area per volume effectively. So it's kind of a weird term until you kind of spell it out that way. So surface area concentration. All right. When we write the terms homogeneous and interfacial, or what I was saying, heterogeneous, individually, the net formulation of I would be the combination of them both. So we can say the integration, the combination of the two would be the integral of RV coming from our homogeneous plus R at the surface, so the surface reaction times that surface area concentration and all that dV. Okay, so what we're saying is for a bulk system, it's a little bit straightforward. We talked about it. It's that reaction over the entire volume that we're interested in. If you think about the building blocks, right? No matter what their state in terms of how well mixed they are, many times we'll assume they're well mixed, but regardless, we need to account for the entire system where reactions can occur. Then, if we have some surface involved as well, we're going to account for how much of this reaction can occur based on how much surface area of that surface we have. Okay, does this make some sense? Got that? All right, one other note here is I've talked about solid and liquid interfaces. We can also have gas and liquid, and I know gas acts like a liquid, but sometimes we'll do things like air stripping. And then we might have water particles being sprayed, and then we might calculate the surface area of the water molecule, it's not water molecules, the water droplets, to get some idea of how much exchange can we get. Sometimes maybe we are taking some gas out of the air into the water, or maybe vice versa. And so that exchange is a physical process. It'll depend on how much surface area. So the droplet size will be important. Similarly, if we do aeration, the size of the bubbles can matter. How much gas exchange can you get? And what are the rates of gas exchange? Some things like that. Okay. So we have an example problem here that it's a lot, and I was planning to go through some other things. So I'm just going to skim this with you, take a look, and we might come back and revisit this next time. Let me just double check and make sure okay. Okay, so I'm going to give us a general picture of this as kind of a look at it. We're not going to try to solve it. Just wanted to walk you through a little bit of it. I think it paints a little bit of a picture of how we could go about a homogeneous reaction. So when we have when we have drinking water disinfected with chlorine, sometimes we have some organics in the water as well, and that can be a problem because we end up getting halogenated byproducts, so these disinfection byproducts. So specifically, we might be dealing with things like chloroform, chloroacetic acid can be generated. These reactants, it's a diverse collection because usually we have some natural organic matter. If we've got some organic matter, it's a wide variety of stuff. If you think of making tea, you don't know which molecules exactly are in there. You just know there's a lot of brown-colored molecules, and probably lots of them are large, and they have different functional groups if you look at organic chemistry. So it's going to be a wide range of possible reactions where we are chlorinating or halogenating things. If there's bromide in the water, the chlorine can react with bromide, create reactive bromine, and you get even worse disinfection byproducts. So all of that kind of stuff is happening. The kinetics for DBP, that's disinfection byproduct formation, is pretty complex because you've got all sorts of different molecules and all sorts of different reactions. And because the disinfectant can simultaneously participate in many reactions and some that don't form DBPs, the mathematical models proposed to describe it, they're pretty difficult to get a precise one. So one model suggests that the rate of chloroform formation is approximated by a function of the rate equals K times the concentration of natural organic matter times the chlorine concentration, HOCl. K is an empirical constant, and chloroform is essentially inert in the water once it's formed. So the following data was collected in a batch treatment test under conditions where K is estimated to have a value of 3 times 10 to the minus 6 milligrams per liter to the minus third per minute. So then the task is to estimate the chloroform concentration in the solution at 1 hour. So what we have is a batch system, some description of kinetics, some description of what's in there. Don't attempt to solve it, but just think for a moment. Could you, given some data here, and this is providing us natural organic matter, I'm sorry, this is not, can't quite see it, natural organic matter and HOCl concentrations as a function of time. How would you go about figuring out what your chloroform concentration would be at the 1 hour mark? Just spend a minute thinking about that. Where would you start? Okay. Maybe I can adjust that later. Needed are changing over time, right? And so it's not going to be straightforward, and it's not going to be just a simple, okay, find the line of best fit and plug in some numbers. Okay, that's the deal. We unfortunately don't have that kind of situation. I think what makes the most sense to me is to just take a look at what's happening on the graphs. So up here in the top right, this is part A. this is essentially the concentration of natural organic matter and chlorine over time. And we see chlorine dropping a bit. Natural organic matter stays fairly constant. We're not really changing enough of it to make a big difference. So in order to account for the different chlorine concentration over time, over the course of our hour time frame, essentially one option is to make a calculation at each time where we have a measurement and say, at this moment, we've got this amount, we expect this amount of formation. So that's what the solution is suggesting, is to calculate a chloroform concentration given each combination of values here. And so the next one down, the part B here, is the chloroform formation rate in milligrams per liter minute. So we get a rate at each time period. And then, you know, it's still not super convenient because we can't just say one rate over an hour. We have, you know, 6 or 10 different rates, however many we have here. So we have a bunch of different rates. And so what we'd have to do is divide this into chunks. A lot like we were talking about the DV concept, the storage term, dividing our total volume into a bunch of chunks. Well, we could do a similar thing here and essentially say, all right, well, let's figure out how much we would produce given the first 5 minutes of production at this rate. Okay, so let's read just a little bit about what it's saying, and that's kind of the approach. And ultimately, once we do that, we should be able to kind of sum up all of the chloroform we expect to have been produced during that hour. Okay, so back to the book here. It says the data for these concentrations are plotted here. The corresponding rates of formation are in part B. Since the only process affecting chloroform concentration is in the solution is this reaction, and since the concentration is uniform throughout the solution, so it's well mixed, the mass balance can be expressed like this. We've got V dc dt equals V times the rate. And here's where I was planning to have a few slides to elaborate on that. But since it's a batch, we don't have anything going in or out. It's very simple. What's accumulating is equal to what's reacting. Okay. Then we're going to take the integral from an initial concentration, which should be 0, I think, for the chloroform, to the concentration at 60 minutes, and say that's going to be equal to that rate of change over that 60 minutes. So that rate times dt. And so our concentration is going to be integration across the hour of that per time slot. But our dt here is not infinitely small. Here we have big time chunks, and so the best thing we can do with that is to say, well, the concentration at time 60 can be computed as the time integral of the formation from 0 to 60. Although this can't be evaluated analytically, we can essentially estimate it, evaluated as the area under the curve in this figure. So if this is providing us the rate of formation per time, if we integrate the area under that curve, then we should get our amount. So then we can do that, and it says we should get approximately 73 micrograms per liter. Okay, so there's a reason I didn't ask you to just give this a try, only just to kind of think about how you might approach it. And that's because we really, there's a lot going on here. And I'm, again, just trying to get you in the mode of thinking about this type of problem, how we might approach it. Okay, does that make some sense? Possible, seen stuff like this before? Okay. Well, I apologize. I thought I had gotten rid of all the pieces. I missed one. All right, so when we want to combine terms, and I'm just going to deal with it here, we're going to have to combine transport and reaction. if we have to deal with a system that has both. So when we set up a mass balance, a simple approach would be to take just the advection and then a reaction term. So if you see all my markup here, you can kind of see that, well, that's exactly what we have thought about, is if we want to take out all the physical transport stuff that is not our flow rate coming in and out, then we'd get rid of these terms, okay? And again, this is a system we can see because we're integrating, or we're taking the derivative of x. This is just one dimension. So if we need to do this in 3 dimensions, we've got this same term in the y and in the z term. So if we had an imaginary sphere of water, let's say maybe we are just drawing out a marine protected area, and we want to know the mass balance of something going in and out of that area. Well, we're going to need to do the physical transport in all 3 dimensions. It's a little simpler if we have a pipe, and really the most important dimension is with the pipe, in the direction the pipe is going. But you can definitely see these terms can be important in some systems, right? And it's just math to deal with it if we do need to. So the full reaction here, or the full combination, would be to say that the change of our concentration in the volume, in the storage term, over time, that's our net accumulation of our thing of interest, is going to be equal to what's coming in from advection, what's going out from advection, plus anything that's coming in or going out from diffusion or dispersion. And I believe we are writing that essentially with a plus for the outlet and a minus for the inlet. I think there's a mathematical reason we would invert it that way, but we're not going to be solving these problems that way, so don't worry about that. But I think essentially when we're diffusing, the way we describe it might be that positive is going backwards, back out, kind of thing. Anyway, then we have a reaction term, and here we've done the bulk phase, so homogeneous solution, plus whatever's on the surface. And by the way, we could have a scenario where, let's say, chlorine reacts in my bottle, but it reacts especially well at the surface of my bottle. Okay? Then we have the same reaction, but more of it happening in a particular amount of it. So it can be that we have 2 similar reactions, one in each phase. Okay? So there are scenarios where that may be important, or maybe just other sources of production, growth, or decay of some substance. Okay, again, all of that in that dV. So my point here is that there's a lot going on, and we can deal with each piece. In fact, you've had enough math in each of your educations to do the math here. Some of it, if we got really involved, would just take some review and take a lot of writing out of integrals and things to fully do it justice and solve that. So I say all this because we have resources like our textbook. If you do find yourself in a job where you need to handle this kind of stuff, it's there. You can do it. You're capable. It's a thing to do. And if you've taken like a groundwater hydrology type of course, you've probably seen a lot of this type of stuff. That's where this type of stuff is more dominant, and we're going to focus more on our reactions and the reactor design accordingly. Okay, so here's where, what I'm going to do. Let me just check some slides. I grabbed, you'll find this entertaining. I even left myself a note for next time, and I did make these changes. I basically told myself, hey, you should have put some of these slides here instead of over there. And I did that. I did all of that, and I updated it, but the update didn't come through. So I'm going to see if those slides are clean, and I want to essentially walk us through what am I talking about when I talk about the different reactor types? What is an ideal reactor? What are we referring to? What's going on? Maybe, if my computer will behave. No, I took them out of there and they might have just disappeared altogether. Okay, we'll see. I'll figure that out. We're going to continue with what we get. All right, so long story short, and I will elaborate on this next time, we have three basic types of reactors, and then if and when we need to deal with a non-ideal reactor, we can essentially use these three types in sequence or in series or in different combinations to model the non-ideal reactors. So the three types would be a batch reactor, which is just like a bottle or a bucket. Got some water in it, something happening, no flow rates, right? Then we would have a completely mixed or completely stirred tank reactor. You'll hear them called CMRs, completely mixed reactors, CMFRs, completely mixed flow reactors, CSTRs, what I typically use. Anyway, this is a batch reactor, but it has flow. Okay, so it's well mixed. So it's stirred, and it's completely mixed in ideal conditions, and it has flow going in and flow going out. Then we have a plug flow reactor, PFR, and this is like a pipe where we have only mixing within one plug. If we look down here at my old notes, we can identify some plug of water that's traveling through. It's a very small, discrete X distance, and it's completely mixed within that plug, but not with its neighbors. That's important because it's very different than a CSTR. It is continuously flowing because we'll have a flow rate going in and leaving. It's like a hose pipe. If you leave a hose sitting in the sun and it's got water in it, turn on the water, it's pretty hot at first. And suddenly it gets cold because suddenly you've reached the water that's been inside or underground or wherever it's cooler. So it's not mixed from the beginning to the end. Otherwise, it would be slightly cooler from the very start, right? So intuitively, you know this. It's totally obvious. But when it comes to reactions in reactors, that's a helpful analogy, helpful to recognize that the mixing is not happening across this X dimension. Okay, that allows us to have a particular situation. So we can essentially derive from this large mass balance equation simplified mass balance equations for ideal reactors by getting rid of the the diffusion and dispersion terms. And if we assume ideal conditions, then we will be left with something that looks like this. For a well-mixed reactor with a fixed volume, our net accumulation, V dc dt, is going to be the flow that's going in minus the flow going out given their respective concentrations, plus whatever reactions are happening in that volume and on any surfaces in that volume. Okay, so if you've had any of my courses in the past, we've probably done exactly this, but not with the surfaces. Okay, so we have an improved tool there. And of course, like I said, if you need to, you can add in the other transport terms here as well. So then if you do that at steady state meaning within that reactor, we don't have any net accumulation. It goes to 0. Then we have a constant amount of species I within that total volume. Then we end up getting 0 equals that reaction, that equation, and we can simplify it from there. So this is a non-steady state, and then followed by a steady state. Okay, a plug flow reactor is going to be, turns out, quite similar to a batch reactor that we place on a conveyor belt for the period of time that it spends within our reactor. So here we can describe that as 0, and this would be at steady state. 0 equals Q times C in minus C out, plus the integral of that reaction that's happening within that plug's volume, that one little plug's volume. Okay, and what we'll notice is essentially we'll get the same answer in that case as if we had taken a well-mixed batch reactor, so no flow, but we gave it some amount of time. These two will find the same answer essentially. And so in the batch reactor, this is pretty much the simplest case. Our accumulation, we're typically not at steady state unless we have the same rate of production as the rate of decay. It's the only time we'd have a steady state. But typically we're not at steady state, and the accumulation change will be equivalent to what's the reactions happening in the bulk plus the reactions happening on the surface within that volume. And that's it. So we're going to come back to each one of those and elaborate on them. But I wanted to present these to you while we're talking about all the different pieces that can change, because you can imagine in each of these you could put in these terms, right, to any of these equations. All right, so that brings us to these, is it ideal, is it not ideal? What are these residence time distribution systems? And really, I think it would be better if I did get my slides in order like I wanted to give you this. So what I'm going to do is I'm going to spend 2 minutes painting a bigger picture, overview, kind of introduce this topic. We'll go back to reactors before getting into this next time, is my plan. So at the big picture scale, in order to know whether or not one of our reactors are ideal or not, or maybe to measure how unideal they might be, what we want to do is something called a tracer test. And I'll pull up next time a video, if I don't have it in the next slide, where you can watch this plume travel through this little reactor. And what you find is that there are spaces that have better or worse mixing. So you see some little spots where there's maybe a lot of dye, maybe not so much dye, maybe no dye at all. And if, as you watch it pass through, it'll kind of cross this bend, and you'll see there's kind of a dead zone is what we call here. So these are indications that, okay, this reactor is acting like a plug flow reactor, meaning the stuff up here is not mixing with the stuff back here. And it is fairly well mixed across this axis, but certainly not perfect, certainly not ideal. And you can watch some dispersion happening. You can watch the fact that it's diffusing a little bit. And of course, we have the advection going through. So with all of that, a tracer test can give us a way to estimate how close to ideal is it and how much time does our water spend in it on average? So if we measure how long it takes before our molecules come out with a tracer test. So a tracer is something that we can see or measure easily and that is not going to react. So it lets us see essentially the flow characteristics without any concern about reactions. So if we do one of these, what we call a residence time distribution tracer test, we can do a cumulative, how long did it take before all of it came out? Or we could say, okay, how much is coming out at a given time? And those are two convenient ways where we might be able to find and express what's happening in our reactor. Another possibility, of course, is just throwing it in a big computer with computational fluid dynamics and making our best estimate of what's happening in the reactor. That's not always practical, and certainly if you're trying to troubleshoot something that you're not sure what's happening in your black box reactor, maybe a tracer test is a much more realistic approach. Okay, well here are, maybe I just put the slides in a different spot than I was thinking. So this is what I was planning to talk to you about a bit. So I'll go through the reactors and then we'll close with that. So I mentioned these, but we have three types: the batch, the CSTR, and the plug flow reactor. Anytime we are developing a mass balance, we are going to structure it as the net accumulation of something in our volume. So V dc dt is equal to these inputs, and really what I'm referring to is the advection in, if there is. We could include the other physical transport. So these would be the transport terms. Transport in, transport out, plus the reaction terms. So for a CSTR, these would look like QC coming in minus QC coming out. And then our reaction term, which we were describing as in that volume, some rate. Let me just get my terms correct here. So RV plus R at the surface, sigma times A dV. Okay, so that would be the general setup. And for a given reactor type, what's happening inside or which terms we have may change. Then from there is how we are going to essentially derive a given reaction equation as needed. So we could look at reactions where we have varying types of reactions themselves. We could do a first order, a second order, zero order reactions. We could have potentially multiple reactions, just like we could have potentially multiple inputs or outputs. We could imagine that there are two pipes coming into a chamber for treatment. Okay, so it's certainly plausible that we'd have differences than the general ones we looked at. And a large task for us will be to derive a mass balance equation that governs what's happening to the mass for a given system. Okay, that's a big point of this, what we do in this class. Okay, I think I'm just going to stop it there so I can get myself better organized, and we'll talk through trouble. I just noticed it saying reconnecting, so hopefully this stream